Class, I want to do a retake on the video on boundary testing. I want to start with a concrete example instead of trying to start with the theory. So let's take a look at a situation. All right, suppose we have a program for paying. The program has two variables, hours worked and the pay rate. And the specification tells you that when you are working from 0 to 40 hours, you get paid for the hours worked. Between 40 and 60, oh shucks, the pay rate is overtime. So you get paid for 40 hours at your standard rate, and you get paid for 1.5 times the hours above 40. That's the overtime. And if you work over 60 hours, you get double your pay for all the hours. All right? So this results in 3 conditions that you derive from the specification. One is hours less than or equal to 40. Another is hours less than 60. And another hours greater than or equal to 60. And when you test your program, you would automatically just pick any hours that you want less than 40. You might say it's 10 hours. For hours less than 60, you might say, let's be a little different from this, and let's say 50. Hours greater than or equal to 60, you may say 80. And those test cases are okay in a functional way. But boundary testing has to do with getting as close to this value as you can. Getting as close. When you have the inequality less than or equal to, there are 3 ways to get close. One is get exactly on it, right here. The other is to be right next to it on the left. Get as close as you can on the left. That's a 39. The other is to get as close as you can on the right, like a 41. And if I'm close to it on the left, it's true. If I'm on it, it is true. But if I am above this, like 41, I am just beyond the range of the test. Notice that what we're really testing is the points at which the true should change to false and vice versa. So let's take a look down here. For hours less than 60, how close can I get? I can get to 59 rather, and 59 is less. That's the biggest value that's less than 60. What other value do I have? Well, I have 60. 60 is close. What's the problem though? For hours less than 60, like a 59 is true, but if you go to the next number, it becomes false. So I want to test these conditions for both true and false, focusing attention on this value. So if I'm looking at hours greater than or equal to 60, what values do I have? I have a value on the left of it, which is not exactly there, but it's as close as you can get. I have 60. Then I have, am I doing this right? Yeah, then I have 60, then I have 61. A couple of things to notice. When the inequality includes equality, there are 3 things I need to check for. One of them is exactly landing on this value. The other is on the left side, the other is on the right. Depending upon the condition, if I'm on the left side, it's true. If I'm on the right side, it's false. Okay? That's the point that we're having. So what I have shown for you is all these values that are close, that cause this condition to kind of go from true to false or false to true. Those are the test values that I need for the variable hours. So if you look at all the values we have listed here, they really are a set of 6 values. Boundary testing says you must test using these values for hours. Notice that in this problem, we don't mention or we don't place any restriction on the rate. So therefore, there's no boundary situations for the rate. So how do I test using these? Well, a test case is a pair of hours followed by rate, and that's the input. And the third component of the test case is the expected value, which you have to figure out based upon the problem. So the boundary test cases would be 39 paired with a rate value. If there are no restrictions on the rate, choose a value that makes it easy. So in this case, 10. 10 times 39 is 390. I can do the math in my head. I need 40 and 10, 41 and 10. If it's over 40, okay, then it says you got to pay time and a half. So that's how you get $415 here. If I use 59, in the rate 10, it looks like it should be 590, but 59 falls into this overtime rate. So you got to apply the formula for overtime. And finally, if I say 60, what are we supposed to have? Well, the rule says over 60, it should be this. And this also includes 60. No, this says over 60. Over 60, let me not mess around. So the rule that applies here is number 2. So it's the overtime thing. So I get paid for 60 hours plus 10 more hours, okay? So it comes out to $900. Now, if I have 61 hours, then this rule applies. I pay twice the amount of your, I pay you for all the hours, I pay you double. So that would be, I think this is right. Yeah, $12.20. Okay. Now, over here, I want to introduce something that I started with in the lecture, which was not a good idea. And it's the notion of having a pattern for looking at these boundary situations. And the patterns are, they're points of interest. One point is I'm inside this interval that is a value for which is true. If you have equality, I want to land on the value here. And I want to have one point that's outside. That's the point at which this thing becomes true, becomes false. If I have strict inequality, there's only 2 places I can be. I can be in or I can be out. I cannot be at something. And notice finally, the hours less than or equal to 40 and hours greater than or equal to 60 follow the same pattern in that you have an at value, you have an in value, and you have an out value. Because of the inequality, if you list the values in increasing order, the order of in and out may differ because of the inequality. Okay. Okay. And so we can talk in general about your boundary analysis. If you have a inequality, then you know you got to look for 3 boundary points. If I have a strict inequality, you're looking for 2. And so you want to find all of them and put them in a set and say, I must use this set of values for hours for the boundary testing. As we began, we said, if you were testing these, just doing what I call the functional test, and you would pick any value for hours. You might have picked 30. You could have picked any value here. You might have picked 50. You might have picked any value like 100 here. But for boundary testing, you get as close as you can. That's the whole idea. Now, so how do I make my test cases? I've already said that. So let's kind of play with this. Let's try to remember these test cases, and let's try to run this, and we're going to discover some stuff. So let me make another panels vertical. Let's just run this thing. Come on, man. Okay. Now, we're going to try these test cases and see what happens. So we're going to say, remember, we can do this. We can say, I want to use 39 and 10, and I want to pipe it into demo pay C run. Okay. So we see the test case. We expected to see 390. We got 390. Let's do another one. Let's feed it 40 and 10. Let's see what we get. Type in the wrong number. 40 and 10. Okay? 40 and 10. Let's type in 41, 41 and 10. 788. Oh, foot. What's going on here? Is my math wrong? I typed in the wrong number again. I'm not good, y'all. 10, 415, 59 and 10. Let's see what we got. 59 and 10. I get 685. Whoa, whoa, whoa. 59 and 10. Something is funny here, isn't it? Notice that the test result here is different from what we expected, okay? And what does that mean? Well, it means two things. It could mean that you misinterpreted what the program is supposed to do so that your test case is wrong. Or what else could it mean? It can mean that you have the right test case, but the program produces the wrong answer. That could be what's causing that. So let's not try to decide which one it is right now. That's the final test case. Final two are 60 and 10. I get 12. Whoa. 60 and 10, I get 1200. We were expecting 900. That's weird, okay? How many of y'all trying to panic? I'm making mistakes on purpose, so I'm not surprised by what I'm seeing. And finally, we do that. So there are two suspects here. The test case, which test cases are wrong? 85. These two are wrong. What do we have to do? Go back to your spec and make sure you read it right. Boom. Go back to your conditions to see if they represent what the spec is saying. All right? So make sure you clean up the specification. And finally, if the specification is okay, go check the program. All right? I need to say this and be very clear. Black box testing means you cannot look at the code. You don't look at the code. You got to use your brain, and you've got to figure out what the code is supposed to do based on the description of it. All right? Now, if I were to switch real fast and go back over what we did in class today, you can now identify some of the stuff we were talking about. we were saying if we have the inequality, we have the point A, which is at. We have the point next to it, which is out, and the point next to the left of it, which is in. So I'm basically saying the test cases that you need to, the test data that you need to have are A minus 1, A, and A plus 1. There are 3 values needed. If we do, over here it's the same idea. Okay, where am I? I wish I had done this. I wish I had done this interval more, because all of these are kind of based on these intervals. For each operator, this little diagram may look slightly different as to the order in which your ins and outs and ats are. I want to draw your attention to a couple of things. If we're checking for equality, when is this true? There's only one way this is true, is when you're at it. What's the closest value to being true? The closest value on the left, which is A minus 1, the closest value on the right, A plus 1. So there's 2 ways to be false on this. You can be too big, you can be too small. But the goal in boundary testing is you can be too big, but yet you got to be as close as you can get to A. What about not equal? Well, not equal is interesting, because if we use the value A, it's really false. And the true values are really the value next to A on the left and the value next to A on the right. So you have 2 ends. You're in on the you're in on the low side, you're in on the high side, and what we would ordinarily say would be at is really out. What is the point? If you see a relationship like an expression like this, your boundary values have to be A minus 1, A, and A plus 1. How many of y'all noticing that in almost all instances it's A and A plus 1, A minus 1? So that's kind of it. The last thing I want to reiterate is if it's strict inequality, there's only 2 boundary values of interest. One is the one that makes it true, we call that in, and the one that makes it false. So for this, A minus 1 is true, but A is false. Okay. Now I need to say this, and I need you to understand what I'm saying. All of these things I've shown you, like I want to look at a value of A plus 1, A minus 1. This 1 is significant because if I'm dealing with whole numbers, 1 is the right value because integers are 1 apart. The distance between integers is 1. If I'm talking about a float, the distance is not a 1. How close can you get between real numbers? You can get as close as you want to get. For that reason, we introduced later on this notion about precision. It really means how many decimal places. How many decimal places do you want? So if I want to be within 0.01, to me, that's the closest number, which is really 2 decimal places, then I will say my precision is a 2. And that translates to 1 over 10 squared, which is 1/100th. So when you're dealing with floats, you got to be careful so that when you build up your boundary values, you got to say the number plus 0.01, the number minus 0.01. So it would be 5.00, 4.99, 5.01. Okay? That's the only difference. And what you see at the bottom of this is you can build a table of all of these ins and ats for all of your conditions. And you can identify your boundary values that you want to use. And you have a set of values for each variable. boundary values for each one of these, okay? This word should say value, not points, all right? And as we said in class, you can take each one of these boundary values for hours and pair it with a constant value for rate. And as I showed you earlier, use a rate that's a simple rate. The only requirement is that the rate that you use be away from any of the rate boundary points. So in this case, if you use 10, you're safe because there's nothing close to 10 here. Is that clear? All right. And likewise, when you want to test using the boundary values for rate, you need to pick a value of hours that is not close to a boundary. These values that you pick, we call these nominal points. So that when you do that, you end up with how many test cases? You have test cases for each one of these, plus you have test cases for each one of these. So it's the total number of test cases is just the number of boundary points, boundary values for each variable. So in this case, we got 9 and 6. So I got 15 test cases that are boundary test cases. All right. If you try to do the Cartesian product where you just say, I will try each boundary value for hours against all of the boundary values for rate, you'll have 55, 54 test cases, which is way too many. All right. Now, good luck with you. At the heart of this is your decision table and the conditions that you have. You got to look at your conditions and analyze those. I hope this is a little clearer. I feel more better. I feel like I did a better job. And with that, we are going to shut it down. A reminder, if you need something, you better ask somebody, okay? If you need something, go ahead and ask me. With that, I'm signing off.